but I wanted to talk to you guys today about literal equations. Literal equations are equations that are typically made up of entirely or mostly of variables. And, you know, you're probably at this point in your life very, very comfortable with the idea that math is always going to come out with a numerical, solid, calculatable answer. Unfortunately, that's not the case. Math sometimes lives in this world of abstract, in this place where we're playing just with letters. And there's often very good reasons for why we do this. Physics, in particular, is usually, as a science, best accomplished when we look at things from the variable side of things, solve that to the point we want it to be at, and then plug numbers in after. You'll get what I mean in a second. I'll show you a couple of very specific examples of how this was used. But the idea is that we use our algebra rules to deal with these variables, because variables can play nice. They can be moved around as individual packages using our algebra rules in order to isolate maybe one or two specific variables that we're looking for. So an example might look something like this: a, b, x, y equals s, r, t, n. All of those could stand for different numbers. Those numbers could be really easy to handle, like 1, 2, 3, and 4, or they could be really, really nasty. They might be like 23/73, or they might be 0.75, or they might be a negative 2 3/8, right? The more complex those numbers get, the harder it is to move them around and do your calculations. So sometimes, rather than trying to plug those numbers in and calculate exactly what the numbers need to be, sometimes it's nice to say, okay, the thing I want at the end is going to be this letter S. I want to figure out what S is if it's by itself. And rather than trying to plug in all of these complicated numbers and running all those calculations, it might be valuable to just say, what would I have to do to get S by itself? Well, in this case, S is being multiplied by R, T, and N. Opposite process of that multiplication would be to divide all of this by R, T, and N. Divide all of this by R, T, and N. And those are all going to cancel over here. We're left with just S on the right, and on the left we've got whatever A, B, X, and Y is, and whatever R, T, and N are on the bottom. And that would be your solution right there. Don't like that. And that would be your solution right there. Okay. A pretty famous example of this is actually over here on the right. I don't know how many of you are taking chemistry or have taken chemistry or have seen this before in a physical science class. This is what is known as the ideal gas law, right? And you don't need to memorize that. You don't need to have this completely down in your head. But it is an example of something that was taken in science and then used in a very special way. The ideal gas law says that for any pressure, if you multiply the pressure of the gas by the volume, it's equal to a specific number of moles, I believe, multiplied by the gas constant, multiplied by the temperature of the gas. And these two things and this thing here, those were all measurable. N and R usually were a little harder to measure. R was kind of a constant number and depended on the mass of the gas and things like that. One very, very smart scientist said, hey, if I play with these numbers in a specific way, then maybe I can take P, V, and equals N, R, T, and if I divide T on both sides here, okay, I get PV over T equals N R. Well, R happens to be a constant number. It's 0.0821 or something like that. I don't remember exactly what it was. But that's a constant number. And N could be constant. N stands for number of moles, and you don't need to know all the long details about that, but there are ways that scientists have to make N constant for every gas. Which means, if that's true, if N and R are always going to be a constant value using the rules the scientists have to play with, then it's potentially possible for PV over T to end up being constant as well for any one gas. So if I had, let's say, some oxygen, right? And it's oxygen in both cases, but maybe one time I have temperature set at 100 degrees Celsius, and another time I have temperature set at 0 degrees Celsius. Well, what's that going to do to the pressure and the volume? And how does that affect it? So scientists figured out that for any given gas, as long as the gas remains the same kind of gas, these variables end up dropping out, and they can play with these specific measurable things to come up with specific values. And this ended up coming up being the way that several very important gas laws were created. Charles' law, what else? There are a few others. I'm not remembering the names now. That's not really important. You don't need to know all of these specific laws. But this is an illustration of how this idea of moving the variables around first led to important discoveries later. So just by moving temperature, we ended up with this very, very important law that allows us to manipulate pressure, manipulate volume, manipulate temperature, and create resulting differences in the other variables. And scientists found very, very solid ways to calculate measurable differences in these three variables. Another pretty famous example, more in the mathematical side of things, is this particular formula right here. Y'all are probably familiar with it. C equals 2 pi r stands for circumference equals twice pi times the radius. It's the circumference of a circle, right? So if I have a circle with radius, some number, who cares how long that is? Circumference is the distance all the way around. That's what that stands for. So what scientists discovered was C, this thing, is measurable. I can take a ruler, I can wrap it around, I guess a measuring tape, I can wrap it around. I can get this value for C. If I take C and I divide it by R, I divide it by this measurable radius. Again, take out your measuring tape, find out what that is. And then I divide it by 2. Just going to cancel the 2 over here. Okay, so C over 2R. Every single time we do that, regardless of how big or small that circle is, how big or small that radius is, it always gives us this number. This number then became known as pi. It's a constant, comes out to be 3.14. It's one of those things that is a general, consistent value that mathematicians use to measure circles, measure their circumference, measure their area, because it was discovered to be so very reliable.
characters, more battles, more fun. Super Smash Bros. Ultimate, only on Nintendo Switch.
Another really common thing that we're going to be seeing this year, we're going to take an equation that looks like this, and we're going to be manipulating it, solving typically for x. And I'm not going to do this thing now, because it's going to use techniques that we're not ready for yet. But this is another example of a situation where there's lots of variables, and there are things we can do to get x by itself, and that's going to have a lot of very, very useful... In fact, that's going to derive one of the most important formulas we're going to have this year. We'll talk about that later when we come back to it. Not going to do the work now. But that's what this thing is for. That's why we do this process of taking a bunch of variables and moving them around until we have one of them isolated. It's been used before by many, many scientists, many, many mathematicians to come up with very specific calculations, very specific solutions that are very useful to us. All right, so we're going to play around with that a little bit today. Look forward to some actual examples after the break. Okay, hope you had a good break. We're going to look at a plus b over c equals 5. We're going to solve for b. This is a pretty straightforward example. Work through it pretty quickly. We're going to multiply by c. Multiply by c. It's going to cancel out that denominator down there. So we have a plus b equals 5c. Right? And then one more step to get b by itself. We're going to subtract a, and we're going to subtract a. So b is 5c minus a. Alright? Not too complicated, not too hard. Let's look at another example. What if I have something like a equals half ap, and I want to solve for p? Maybe I don't like having p over here with everything else. How would I do that? Well, probably a good first step would be to take the 1/2, and let's cancel it out by multiplying by its reciprocal. So 2 and 2, 1/2 and 2 cancel. So 2 capital A equals lowercase a times p. And this is a times p, which means I need to do the opposite process of that. So let's divide by a, divide by a, goes away. And we end up with 2 capital A over lowercase a. And we have to assume that capital A and lowercase a are different things. Maybe a lowercase a stands for altitude and capital A stands for area, or maybe capital A stands for anchovies and lowercase a stands for apples. I don't know. I don't know what it could be. But we're making the assumption that because they're two different cases of letters, they're going to be two different values. We can't actually cancel there. They're two different numbers. We don't know if they divide. So we're going to leave that as our answer. 2a over a equals p. Okay? If you have any more questions about this, be sure to ask them in the comments or send me an email. Request a Google Meet. Any one of those strategies would be fine. Thank you for your attention today. Hopefully you do okay on your homework.